Now this one, our volume is given to us with a base of uh, y squared, y is equal to x squared, and we've got our cross sections being right angled isosceles triangles. And this time it's going along the xy. It's perpendicular to the y axis. So our, we've got delta y there. Our base then is we get our triangle there. Our base would be 2x across because x in that direction, x in that direction for the same value of y, which means our height would be 2x. We're cut off here in the shade area at 4. So it's between y is equal to 0, y is equal to 4, delta y. So an area would be a half times 2x times 2x, gives you 2x squared, or 2y because y is equal to x there. So our integral there, and then we've put it in terms of a there if you wanted. Doesn't really matter what the variable is. So we know we're going to integrate 2a or 2y with respect to the thickness there. Integrate it, we get a squared between 0 and 4, gives us 16 units cubed. So in this, in question 6 here, we've got cylindrical shells there, and we rotate, it's going to be rotated around the x-axis, which means our thickness is going to be delta y. There's our delta y there. We can not move it around. The delta y is there, and we've got an area between the curve this time. So what we've got to consider is where the distance between the curve is at all these points, and we're going between 1 and 4 there. So our values there would still be 1 to 4 there. So you can see where our points of intersection. So because we're going to be delta y, we're going to be dealing with those as our limits of integration. The trick here, it's going to be radius of y no matter, we pick a point there at y, so it's going to be up y all the time. But it's the height that we're going to get this time that's the trick. And it's the difference in the two x values. So x1 minus x2, so if this is going to be x1 and this is x2 there, then the value of y here when we manipulate it, we get x1 being root of y plus 2, and well, this one is x, y is equal to x, so that would just be y there. So that's where we're going to get our limits of integration. So you can see there's more manipulation there. The y plus 2 minus y, delta y with a 2 pi y between 1 and 4. So it gives us, multiply through by the y there, we get y power 3 on 2, 2y and minus y squared. And that's what we're going to integrate. Put 1 and 4 in, and we get 64 pi on 5. Question 7, we're rotating with this time, and it's an ellipse here. It's rotated around the axis, and as you can start to see, we start to get an annulus. So an annulus is a little bit tricky in this case. We're looking at our two radii, and we're going to, because we're going around the y-axis, we're going to have a thickness of delta y. So that's going to be what we need to get our functions in. So when for any particular value y, we're going to get two values of x there. And so if we solve for x, for any particular value of y, we have to take the y squared on 4 across, and then we take the square root. So we're getting the positive and negative square root, and then x is 1 plus 1 square root of 1 on y squared on 4, and then 1 minus the square root of 1 on minus y squared on 4. So there's our two radii that we're going to get. So if we do it, there's our volume function we're going to play with. And if we do that manipulation and do the r squared on r2 squared minus r1 all squared, which you get from that, you start to get well, that part back to that part, and then you can simplify, and it simplifies it down when you do the working out to 2 outside the square root of 1 minus y squared on 4. So there's that manipulation we get there. So that's going to be our area of the semicircle as such. If you look at that, you can calculate that. You can do the substitution and get your volume there, but if you recognise that, it's often a good trick to recognise that as the area of the semicircle, as we've seen in some of our questions before that we've been doing. -2 to 2 of square root, that's just finding the area of the semicircle. So radius 2, so it's easier than doing all this work, which you can do because it's just a trig substitution that we need to do with that with the integration. But that gets us down to, will get us a much easier answer of our volume as we. So keep that in mind. If you see that, then feel free to use it. You don't have to do the integration if you can recognise the area of the semicircle.